Hello everyone. In this video, we are going to talk about chapter 18, section 18.5. This section right here, we're gonna looking at things from the energy perspective. So basically, principle of conservation energy says energy is initial energy equals your final energy. Okay, so we're gonna add in the potential energy and we're looking at the conservation of energy together. So starting with some definitions, conservation of energy theorem is simpler than the energy method. We recall that principle of energy, working energy is also an energy method for solving problems. Once again, the problem parameter of distance is the key indicator for when conservation of energy is a good approach to solving a problem. If this is appropriate for a problem, conservation of energy is easier to use than the principle of working energy. This is because calculating the work of a conservative force is simpler. So when a force is conservative, if the work done by the force is independent of the path. In this case, the work depends only on the initial and the final position of the object, with the path between the position of no consequence. Typically, conservative forces encountered in dynamics are gravitational force and the elastic force. Under the second page here, when the rigid body is acted upon by a system of conservative forces, the work done by these forces is conserved. So the sum of kinetic energy and potential energy remains constant. This principle we call it the conservation of energy. So basically, initial total energy, we have total energy initial, total energy final should not be changed. That should be a constant. In other words, as a rigid body moves from one position to another, when acted upon by only conservative forces, kinetic energy is converted to potential energy and vice versa. Gravitational and potential energy of an object is a function of the height of the body of the center of gravity, above or below the reference datum. The gravitational potential energy of a body is found by this equation. Vg, gravitational potential energy, equals weight times yg. Over here, yg is the how far are we away from the reference point, the datum. This yg will be positive if it's above the datum. Yg will be negative if it's below the datum. Spring force are also conservative forces. Potential energy of a spring force F equals Ks is found by this equation. E stands for elastic. That's 1/2 Ks squared. And notice that the elastic potential energy is always going to be positive, regardless if the spring is being compressed or being stretched. Problems involving velocity, displacement, and conservative forces can be solved using the conservation of energy equation. Potential energy, we draw two diagrams, one with the body located at its initial position and one at its final position. We're going to calculate the potential energy at each position using V equals Vg plus Ve, where Vg equals Yg, Wyg, and the Ve equals 1/2 Ks squared. Kinetic energy, we're going to calculate the kinetic energy of the rigid body at each location. Kinetic energy has two components: translational kinetic energy, 1/2 mv squared, and then the rotational kinetic energy, which is 1/2 ig omega squared. And then we're going to apply the conservation of energy equation. Let's take a look at some problems together. This thing says AB has a mass of 30 kilogram, spring at 45 degree, at 45 degree theta equals 45 degree, spring is unstretched, and the spring constant K is 300 Newton per meter. We're looking for the angular velocity of rod AB at theta equals 0 degree. If the rod is released from rest when theta equals 45. If we taking the reference point of datum to be in the middle with the rod at 45 degree, then the gravitational potential energy and the elastic potential energy will be zero at position 1. So at position 1, we set the position 1, where the center of gravity is, we set that to be the datum, and also plus at that 45 degree, the spring is being unstretched. So at that position 1, initial position, your elastic potential energy equal to 0, gravitational potential equal to 0 as well. Okay, so V1 equals 0. So at location 2, when we have this thing at 0 degree, potential elastic potential energy. So now the spring is being stretched when this thing is flat on the ground being stretched, and this thing right here is calculating how much it's being stretched. Plug that into where we calculate the elastic potential energy. So this is how much is being stretched, and then square 1/2 mass times stretched square. So this gives us the elastic potential energy. And then gravitational potential energy, we're going to calculate how much it's being going from the datum to the floor, to the 0 degree. So this is vertically how much it's being, the center of gravity, the location of center of gravity changes. And because it's coming down, it's negative. So you have negative 30 times 9.81, and then 1/2 of 1.5 sine 45. That gives us the uh, gravitational potential energy, which is negative. Putting that into the, let's see, hold on. Keep going at position number two, we also coming down, we have some velocity. And this velocity right now, it's both translating, it's rotating as well. And we have an equation that this is your translational kinetic energy, and this portion is your rotational kinetic energy. And putting that together, we can relate the linear velocity and the angular velocity together into our equation. That will give us the final kinetic energy overall. And we put that into our conservation of energy equation. Initially, we have a zero, and then finally, we have the potential energy, uh, gravitational, elastic together, and we also have what is it called? Uh, Kinetic energy. Um, we have our kinetic energy translating, rotating together. That will help us calculate the omega, the angular velocity at 0 degree. Next one, we have a 30 kilogram rod released from rest at 0 degree. At 0 degree, spring is being unstretched. We're looking for the angular velocity at theta equals 30 degree. So what we're going to do, still same thing, we're looking at datum as being 0 degree. That means at 0 degree there's no potential, no gravitational potential, and since spring is being unstretched, there's no elastic potential either. So at position zero, the theta equal to 0 degree, there is total overall is zero. And keep going, since 30 degrees down, we can calculate the center of gravity, how much it's being changed. That will help us calculate how much potential energy we have, and it's negative because we're coming down. And then elastic potential energy, same thing. We're going to calculate how much the spring is being stretched. So basically, using this triangle, we want to figure out how what was originally up here, right? It was up here with a spring like this. How long the spring was initially is 0.5, because if I put that 1.5 up here, so from here to here is the rod, 1.5, and if that total is 2 meters, that means initial relaxed position of the spring is 0.5. That's what this is. And then calculating, also using this triangle 30 degree, and then you use either lot of sine, lot of cosine. However, maybe a combination of them. We're going to calculate the length of this triangle right now, which is the current length of the spring. And then put that together, we can calculate the elastic potential energy, elastic potential energy um, at 30 degree. And keep going. We know coming down is going to have kinetic energy as well. The two parts, translational kinetic energy and rotational kinetic energy. And put relating the linear velocity and the angular velocity together, we have kinetic energy, rotational and translational. Put that together. Initial total energy is zero. We have kinetic energy, and there's also the gravitational potential energy and the elastic potential energy. One equation, one unknown. We're solving for the angular velocity. Next problem right here, we have this cylinder at a 6 kilogram bar AB 6 kilogram, horizontally at rest, and the spring is being unstretched. Length of 1.5 meters, and the spring constant 12 kilonewton per meter. We're looking for the angular velocity of the bar when it has rotated clockwise 45 degree after being released. So same thing, if we keep our initial position position 1 potential energy is 0 and the elastic potential energy is 0 as well. That's my initial energy. That's there's no kinetic, right? There's only the initial potential is 0. We let it to be 0 because we set that reference point to be where the position 1 is. And then also the spring elastic potential energy is 0 as well because the spring is being relaxed and unstretched. And then that position 2 is where we're looking at 45 degree. At 45 degree, we can calculate the elastic potential energy, like we drop down 45 degree, but keep in mind that we're looking at how much the center of gravity dropped with that 45 degree. Okay, so don't use that 45 degree directly. So we have gravitational potential energy, which is negative, and there's also the elastic potential energy. And keep in mind that at that moment, it is being stretched, so we're coming down. We have our the spring length. We calculate the spring length at position 2 at 45 degree, and then the calculate how after we know how much is being stretched, we can calculate the elastic potential energy at location 2. And then keep going. At position 2, we know this thing's got a velocity. We're translating with rotating at the same time. So putting those together, no, hold on. It's rotating only. It's not translating, okay, because it's fixed at point A. So we only have rotational kinetic energy. Plot that in. Ooh, I was almost get that wrong. Okay, so only rotational kinetic energy. So rotational kinetic energy plus the potential gravitational potential energy and elastic potential energy. That's the total energy at position 2. Initially, it was 0 when equation 1, and then we're solving for the value of angular velocity. Last problem of the day of this video. So we have a block. We know the weight of the block is 250 pounds and is released from rest when the spring is unstretched. So right now, spring is unstretched. The drum has a weight of 50 pounds and has a radius of gyration k0 equals 0.5 foot, and it's the center of mass O. The velocity of block after it has descended 5 feet. So in other words, this thing is coming down 5 feet. One thing is that you notice the block is attached to the outer radius of this pulley, and the spring is attached to the inner radius of the pulley. So what we're trying to figure out is, hey, when this thing come down 5 feet, how much stretch do we have on the spring? So what we're doing over here is that we're calculating 5 feet coming down 5 feet. We convert that 5 feet to how much radius, how much degree of angle in radius, how much radius do we turn of this pulley, and how much we turn on that angle is the same thing. No matter you're looking at the outer pulley, outer radius, or the inner radius. So the spring elongation over here, after we get this much angle that we change, we can figure out how much multiply by the inner radius of the pulley of here. So we figure out the spring when the block comes down 5 feet. That means the spring is being stretched 2.5 feet. So that's that. Coming down 5 feet, we know the gravitational energy changes, and we from the how much the spring is being stretched, it should be 2.5 square, not 2.25, 2.5 square. That should be a superscript of that too, and this is helping us calculating how much elastic potential energy we have on the pulley and then on the spring. Okay, initially kinetic essence is at rest, kinetic energy is 0, and then at location 2 we have 1/2 mv square, 1/2 I omega square. We have the translational kinetic energy of the block, and then rotational kinetic energy of the disk. And calculating the value of I, we're putting all of our energies together and relating the linear velocity and the angular velocity. We putting our equation together, total initial energy and total final energy. We calculate for the velocity of V at location 2. Okay, that's all I want to share with you in this video. I hope you find it helpful, and thank you for watching.